Hello everyone, welcome to my video report about Lab 1, the constant velocity. According to the Newton's first law, an object will stay in a state of rest or moving in a constant direction with constant speed when there's no force applied to change its state. However, an object on Earth moving in absolutely constant velocity is almost impossible. So the mission of my report is to visualize the idealistic motion of constant velocity using computational model and capture a motion in period of time that the motion is closer and closer to the state of constant velocity. Here's the major section of my report. First, I will display both the computational model and the observed result. Then I will compare the two and expect possible future improvement. Finally, I will draw a conclusion based on my lab and answer the two additional questions. As indicated by Newton's first law, an object moves in constant velocity when it has no interaction with the surrounding, so the net force must be zero. In order to make the motion of an object closer to the state of moving at constant velocity, I try to minimize the net force. Since I put the ping pong ball on the table and try to capture the motion, on the vertical direction, the gravitational force and the normal force point absolutely and cancel each other out. The only force that matters is the frictional force that will prevent the object's motion. To reduce the effect of frictional force and improve accuracy, first, I choose a ping pong ball as the object because the rolling friction is much more smaller than the sliding friction. Second, I choose a relatively smooth table, and last, I clip the middle part of the video to analyze motion, trying to avoid the accelerating and decelerating part. This slide shows the observational model I constructed. The origin of the coordinate system is the center of the ping pong ball at its initial position. The position and time plot shows a roughly upward sloping straight line, proving that the model simulates a constant velocity motion. The next step is to extract the required data to construct the computational model. According to the Newton's second law, the final velocity minus the initial velocity and divided by the delta t equals to net force divided by the mass, which is also the acceleration. From this equation, we can obtain the velocity updated formula. And according to the average velocity equation, we know the average velocity equals to the final position minus the initial position and divided by the delta t. And we can gain the position updated formula. In this case, we assume that the average velocity is roughly equal to the final velocity. And in order to construct the computational model, we have to obtain some data from the observed model. First, the initial time is 0 second. Initial position is 0.0000524 meter. And the estimated initial velocity is roughly equal to the initial average velocity, which is that you divide the first two rows, the delta x divided by delta t is equal to 2.33354 meters per second, and the final time is 0.8 seconds. Now that I use the data and constructed the computational model, I assume that the ping pong ball's mass is approximately 0.038 kilograms, and I insert the initial position and the initial velocity, and the time period is 0.8 second. And since it moves at constant velocity, the net force is 0, and I insert the velocity and the position updated formula. This is the result of the computational model. And then I use a comparison between the observational model and the computational model. There's the similarities. First is that they are started at the same point and both upward sloping straight line. But there's obviously some difference. The observed line is relatively lower than the computational line, and the observed line is not a strictly straight line. The reason for this is first, the frictional force is still existed because the table is not that smooth enough, and which will prevent the ball from moving forward, and the line will relatively lower. And second is the discrepancies generated when marking the point of mass. I mark it manually, so it's very likely that there's some errors generated. And the position of the phone is not strictly parallel to the moving trials because I fixed the phone on the table, and it's very likely not parallel to the trial of the ping pong ball. So I need make some future improvement. First is mark more frequently the change of point of mass to make more accurate plot of the motion. Second is to choose a smooth plane. Ideally, I want to use the very large ice plane to reduce the frictional force. And third is instead of giving the ping pong ball a force by myself, I want to use a string that can give constant and precise force to the balls. In order to do this, first I have to calculate the frictional force beforehand, and then I will make the string contracted to the length in which the string force is equal to the friction force, and then it put force on the ping pong ball. Here's the two additional questions. First is, what if you flip the axis? Flip the axis means that you flip the positive and negative directions, but the constant velocity is the same. The only difference is that it would be a downward sloping straight line. The line that is reflected the graph, the original graph that I built about the x-axis. And the second question is what it means. Can you calculate how many push and pulls to add in order to give a zero net force? In order to give a zero net force, the force I exerted must be equal to the frictional force, and the rolling friction force is equal to the coefficient of rolling friction multiplied by the normal force. Since the normal force in this case is the weight of the ping pong ball, so if I know the coefficient, I can know the frictional force. Here's the conclusion. First, the position time graph of an object moves at constant velocity is upward or downward sloping straight line, based on the axis you choose. And the second is that the observed model roughly corresponds to the computational model, but the effect of frictions and experimental issues cause a slight difference between each plot.